I'm Colin Coyle from the University of Vermont. I'm excited to present my work with Nick Cheney, What Makes Freezing Layers in Deep Neural Networks Effective, a Linear Separability Perspective. Our work examines freezing layers in neural networks, blocking gradient updates to certain layers throughout training. We refer to frozen layers as reservoir layers, and networks with frozen layers are called reservoir networks. Other scholars showed that freezing layers in multilayer perceptrons and transformers improves generalization and speeds up convergence. But why? Scholars have justified this using Cover's theorem, which says that random, nonlinear transformations into equal or higher dimensions increase the probability of linear separability. Intuitively, frozen layers act like kernels. They map data into higher dimensions, leaving trainable layers to find simple separations. However, we are unaware of empirical testing to confirm whether Cover's theorem explains the benefits of freezing. We fill this gap by exploring the connection between freezing, linear separability, neural architecture, and network performance. We build multilayer perceptrons in three-layer blocks: a trainable layer, a scaled layer, and another trainable layer. In reservoir networks, the middle layer is frozen. We performed architectural sweeps varying hyperparameters including layer width and scaling vectors. These two hyperparameters directly relate to Cover's theorem since they control dimensionality of the transformations. For each architecture, we train 25 fully trainable and reservoir networks on MNIST, CIFAR10, and CIFAR100. We track accuracy and extract hidden states to train linear probes whose accuracy measures linear separability. Here are our width sweep results. Reservoir layers, scaled by a factor of 2, appear at indices 1 and 4 and are marked by vertical dotted lines. The curves' colors indicate network width. Solid lines represent reservoir networks, and dotted lines are fully trainable ones. Both MNIST and CIFAR10 results show that wider networks have higher linear separability scores. The jump in scores between layers 0 and 1 in reservoir networks confirms that frozen layers improve linear separability, supporting explanations using Cover's theorem. But here's the interesting part. Reservoir networks on MNIST perform worse than fully trainable networks. However, on CIFAR10, reservoir networks with more than 32 neurons per layer outperform their fully trainable counterparts. So although some separability trends align with Cover's theorem, a lot remains unexplained. Why does freezing depend on the dataset? Why do small CIFAR10 networks not benefit from freezing? Therefore, we find that Cover's theorem is not a complete explanation of why freezing helps neural networks. For the full paper, which includes more evidence of Cover's theorem failing to explain architectural and data-dependent benefits of freezing layers and how freezing works as a regularizer, see the link in the description and come see our presentation at AutoML 2025.